Hello, everyone. Welcome to my talk. I'm Nam from Pinterest, and today I will present 7 millions from millions, navigating towards cost efficiency for Pinterest Spark jobs. A little bit about myself. I'm currently a software engineer in Pinterest. I work in batch processing platform there, and I primarily focus on build a Spark on Kubernetes ecosystem, optimize our job cost, and also build a data infrastructure for faster AI and machine learning iterations. I'm also involved in multiple open source projects. I'm known as a coding cat in GitHub. You can see from my hoodie. And previously I worked on Apache Spark and later on Iceberg, and recently I focused on Apache Calibre. And for today, first I will briefly introduce the Spark platform in Pinterest. And then I will talk about what are the real challenges we face with when we talk about managing the cost in Pinterest for Spark jobs. And to address this cost, we have multiple layers of solutions, ranging from how we improve the debuggability of cost issues, how we build platform innovations which are the general solutions applying to all of our Spark jobs, and how we build a fine-grained cost management strategy for those very, very expensive or very, very challenging projects. And finally, I will give a summary about this talk, and happy to take any questions. First of all, Spark platform in Pinterest. Basically, our platform consists of 3 layers, client platforms. These are the channels for our users to submit Spark jobs. They can submit as a scheduled pipeline. They can use the interactive notebook. They also submit SQL queries based on Spark SQL to our servers, job servers. And a bunch of our customers build their own platform on top of ours, like our machine learning platform team build the feature backfill platform on top of Spark. And the next layer is the Spark submission servers. We have 2 types of submission servers. Submit our Spark jobs to Hadoop cluster and Kubernetes cluster respectively. And currently we still have two types of cluster here, Hadoop and Kubernetes. We build these clusters on top of Amazon EC2. And you can imagine we are actually in the middle of consolidating our Hadoop cluster into Kubernetes. So when you open the Pinterest app, the experience you have is basically backed by a lot of sophisticated machine learning models. Why you see these pins are in your first page, why you see these ads instead of those. So all of these are backed by those machine learning models. And to build these large-scale machine learning models, you can imagine there will be tons of data processing work. And all of these use cases are built on top of Apache Spark. And because we have so many use cases, we have one of the largest Spark platforms in this world. We have 60,000 workflows running our system, and we have tens of thousands of computing nodes ranging in more than 30 computing clusters. Every day, we have hundreds of thousands of Spark jobs, and these Spark jobs are also very big. They process hundreds of petabytes of shuffle and input every day. And most importantly, our usage is actually growing on a daily basis. And because of this fast growth, we are facing significant challenges in managing our Spark job cost. First of all, as I said, we have very fast growth of our Spark usage. For some months, we can see up to 3 to 4% of usage comparing to the earlier ones. And we also have so many use cases. User can submit pure Spark SQL jobs, which are mostly user resources with those built-in Spark operators. And some of complicated Spark jobs consist of some memory-heavy user-defined data structures that requires a lot of on-heap memory for them. And we also have complicated jobs like the mixed Scala and C++ code that have a very different resource usage pattern than others. And also we have so many jobs. Every week we need to deal with probably not millions, just tens of millions of jobs. So our goal here is how to save X of millions of dollars from these millions of jobs. We build a holistic framework addressing all these cost-efficient challenges. First, we improve the cost debuggability. And second, we build some general solutions in our platform level. And in this talk, I will mainly talk about how we optimize the shuffle performance with the remote shuffle service, and how we use burst-aware memory allocation algorithm to save our allocate resources to more Spark jobs with less memory spaces. And I will also talk about how we apply the fine-grained cost management strategy for those like very expensive jobs, and how we scale this with some work-in-progress project called managed job set. First, how we improve the cost issue debuggability. The goal for us to improve the cost debuggability is basically to surface the root cause of cost issues. First, for different scenarios, whether too high cost is caused by oversupplying the resources, whether there are some logic implementation becomes the bottleneck, or whether the efficiency is caused by some platform components. We need a tool to identify these issues and help our engineers to address them. And also, we need a tool for different audience. Our audience can be platform engineers, which develop general solutions to improve the cost efficiency of all Spark jobs. And we also need to help our Spark users who are primarily focused on individual job tuning. To achieve this, the key is to improve the Spark job observability. We have two types of metrics extracting from all the Spark jobs. The first type is called real-time metrics. We can use the built-in metrics source in Spark, like a JVM source, executor source, and we also have some customized source, like a periodical thread dump, to help us to identify issues like oversupply the resources, logical bottleneck, and we use real-time metrics mostly for individual job tuning. Some examples of real-time metrics we collected, like memory utilization, GC states, and target and allocated number of executors. We also monitor shuffle performance with the metrics like fetch failure to avoid too-many shuffle retries. We also have some work-in-progress project, like periodically generate the snapshot of thread dump of those stack tasks, so that we can find the bottleneck of those implementation. Here is the example about how we use real-time metrics to identify cost issues. In this graph, we can see the JVM RSM memory. We see how much memory we allocated to on-heap space and how much memory we really use in on-heap space. You can see for majority of these jobs life cycle, the on-heap usage is pretty low. So that indicates us we can potentially split this job into two jobs. And the first one only needs a very small amount of memory. And the second one, probably you need to allocate more memory for that. But even for the second one, in the peak usage, there is always a gap between the allocated on-heap space and the used on-heap space. That means we are actually oversupplying this memory space. So this graph can clearly show to our users that you need some tuning or refactoring of your job. The second type of metrics we collected is through event logs. Event logs are essentially the JSON files generated by Spark. If you use Spark, you know there is a Spark history UI. Basically, event logs are those JSON files. We use built-in event log source like to capture events like task end, stage end, and persist the associated metrics. We also develop a lot of customized event log source, like we track the shuffle data expiration rate, aggregated GC data, and for such like event logs generated metrics, we use the ingestion pipeline to parse these JSON files and save that as a Hive table. And we use that for platform-wide analysis, and also extract the trend, for example, for a long period of time. And for such metrics, we mostly use them to develop like general solutions for all Spark jobs. Here is the example about how we leverage this event log generated metrics. The background is that we have two types of CPUs in our cluster. One is ARM, the other is Intel. And ARM CPUs are cheaper, but for those jobs which requires very powerful, like a per core or core computation. For example, some jobs need a regex matching. With our observation is that Intel CPUs usually does better job than ARM. So the challenge here is we have millions of jobs every week. How we can effectively identify which jobs should be run in ARM CPU to save cost without sacrifice the performance. The solution here is to have capture the Spark internal accumulator called executor CPU time. It's based on the JDK API thread max bin to track the on CPU time. And this accumulator can be captured in the task and the event. So here is our architecture. First of all, we define a matrix called CPU intensity. Basically, that's the sum of all the on CPU time for all the tasks and divide the total task durations. And when Spark job is running, when task is finished, the event log listener will capture that and save the JSON object containing that executor CPU time to the, for example, to S3. And then we persist that JSON file, we parse that JSON files and persist that Parquet load as a Hive table. And eventually we can run this query to have analysis over millions of jobs and sort them and know, the top ones should be run in Intel because they have very intensive CPU computation. And for the bottom ones, they don't use CPU intensively, so they can easily be routed to ARM cluster to save our cost. Based on the improved cost debuggability, we can develop a lot of platform innovations to help to cut the cost for majority of our Spark jobs. So the first platform innovation I want to talk about is how we optimize the shuffle performance with the remote shuffle service. Our story started with some customer reports. They say, oh, our Spark job is just so slow and it runs for more than 24 hours. It takes us a lot of money. And when we look at them, we find that these Spark jobs are slow because they spend more than 80% of time just reading shuffle data. And we go deeper into that, we find most of these Spark jobs just run in yarn with the external shuffle service. And the root cause of the slowness is that they have a large number of mapper tasks and a large number of reducer tasks. When the reducers need to read the shuffle data, it actually creates a M times N format connection. That really saturates our cluster network. And to resolve this problem, we introduced the remote shuffle service we want. The idea of remote shuffle service is basically, instead of saving the shuffle data together with your computing cluster, it uses a dedicated cluster to save that. And for every partition of the shuffle, it saves in different workers. In this way, when we have N reducers to read the shuffle data, you only need to establish N connections. That will avoid that format connection problem. So it seems that our shuffle read problem has been resolved. However, later we observed our shuffle write performance becomes very, very bad. For some jobs with a high number of partitions, up to like more than 70% of task running time is spending in shuffle writing. So we have a deep analysis of deeper analysis of the root cause. We find that in the client implementation of our remote shuffle service V1, which is based on one of the earliest open source solution for remote shuffle, it just creates the buffer time and time again. So it spends part of amount of CPU time in create query serializer strings. That makes everything so slow. So we decided to switch to a new version of remote shuffle based on Apache Caliban. Apache Caliban is the open source project started by Alibaba Group. It integrates with multiple computing engines, and it is used by many peer companies, including LinkedIn, Stripe, and it also has a very active open source community. In Caliban, we use a sort-based shuffle writer, so all the partitions data share the same buffer. When the buffer is full, it just send each partition to different workers. And it doesn't need to create the buffer time and time again. So it doesn't have the problem of remote shuffle service we want. And this is very lightweighted to maintain these buffers. And when we compare the performance of Caliban and Yarn external shuffle service, and also our first version of remote shuffle, we find that the overhead brought by the remote cluster of Caliban is ignorable. And comparing to our first version of remote shuffle, it just significantly improve our shuffle write performance. This is an example about one of our production jobs which get a significant benefit when we switch that to use Caliban. You can see right after we switch to Caliban, the cost just reduced significantly. So because we have dedicated hardware for remote shuffle service, where remote shuffle service itself become a cost center. So due to time limitation, I will not go into too many details. The basic idea is we can offset the cost with other innovations in our cluster, like a burst-aware memory allocation algorithm. I will talk about that immediately after this part. We can use the cheaper CPUs. We also contribute a lot of features for Caliban in Caliban to open source community to save the cost of running such a Caliban cluster. And we have some upcoming engineering blog to talk about some new features we just developed. We can run 4 petabytes of KVS join with only like 200 terabytes of disk footprint. That's a significantly saved our cost. So the next platform innovation I want to mention is the burst-aware memory allocation algorithm. Our customer complained to us saying that, so why my Spark jobs cannot get enough resources? And when we look at the metrics of our cluster, we find that our computing cluster just frequently get overloaded. In this graph, the red curve is the allocated memory percentage, and the green one is the used memory percentage. We find that for this cluster, frequently all the memory are allocated to these Spark jobs. But if we look at the green curve, we find that there is a big gap between the allocated and the used cluster memory. That means our cluster is underutilized. Even our customer is complaining we cannot get enough resources. To address this issue, we implement a burst-aware memory allocation algorithm in Spark. This idea is inspired by an academic paper from ByteDance in last year's VRDB conference. So it's primarily focused on optimize the allocation of memory overhead, which is specified by spark.executor.memory overhead. And the observation is that for use cases of memory overhead space, like direct memory, serialization, deserialization, compression, all of these show very dynamic usage pattern. You will not serialize, deserialize data in the whole running time of your Spark job running time. You just do in some phases. So when you are not serialize or deserialize data, this memory overhead space just wasted. So how to address such a burst memory demand in Kubernetes cluster? We can leverage the concept of request and limit. Request just means how many resources you need to get your Kubernetes pod be assigned to a particular machine. And the limit means after your pod is assigned to that machine, what's the max size of resources you can use? For example, if I have a pod have a request of 128 megabytes and a limit at 256 megabytes, that means any node with more than or not less than 128 megabytes free memory can be a candidate for hosting this pod. But after this pod is assigned to a host, it can use as much as 256 megabytes before it's killed by OMKiller. Applying this concept to memory overhead space I just talked about, the idea is that we can split the memory overhead space into 2 parts, fixed memory overhead and bursted memory overhead. And when we applying resources for our executor pod from Kubernetes, we use the on-heap space, which is the fixed part, and plus the fixed memory overhead to get a resource allocation. And then the bursted memory overhead will be shared among all the pods in the same host. The assumption is that it's very rarely for all the pods in the same host to ask for max size of memory overhead at the same time. So we can share some kind of time sharing some memory space in a host. Here is the example. By default, Spark just sets the same value for request and the limit. And if we have 100 gigabytes of memory space, and we have 3 executor pods, and we can at most just allocate 3 pods. First one needs 50 gigabytes, second 40, and the third one 10. But if we can split this memory request, this kind of resource request into request and the limit part. For example, the first one only needs 30 gigabytes to be allocated, second one needs 24, and the third one needs 6. And we can allow these pods to use as max as the original size. For example, the first one, you need 30 gigabytes to be allocated, but you can use as much as 50. Then we can use the same size of memory space to host more pods. For example, in the bottom of this example, after we allocate the original 3 pods, we can squeeze another pod into this host. For example, that's also 6 gigabytes as a request and 4 gigabytes as a limit. 10 gigabytes at the limit. So that will save us a lot of memory space to allocate to more Spark executor pods. After we applying this algorithm to our cluster, we saw it benefited a lot about our resource problem. For example, here, after we launched Canon for this Canon in this cluster, there are less opportunities for our cluster to be overloaded. And even when the cluster is allocating 100% of memory space to all the Spark executors, the gap between the allocated and the utilized memory is way smaller than before. So this is the second platform innovation we have, burst-aware algorithm, burst-aware memory allocation algorithm in Spark. And the next part is fine-grained cost management. You may ask, you have made a lot of improvement in your platform. Why you still need to have such like a fine-grained cost management? That's because some of our Spark jobs are just so critical and so expensive. Even we apply those Canon, the burst-aware memory algorithm, we optimize its sharper performance. It's still like it takes our millions of dollars to run that Spark job every year. And for example, 3 out of our tens of thousands of daily Spark applications actually contribute 2% of our overall data computing budget. And the other case is that our customer can be in a very urgent project. They need to run like a mini experiment every day, but they don't have enough bandwidth to manage the cost at the same time. They also need our help to have some fine-tuning or fine-grained management for their cost. They just focus on business implementation. So we have some powerful tools for fine-tuning. The first one is look at the memory utilization. This is part of the real-time metrics that we collected from different metric sources. In this case, we look at the memory utilization. We find even the customer's Spark job executor has used 100% of allocated memory space, but the GC is pretty lightweighted in there. That means we can probably let JVM GC to do more job and squeeze the allocated on-heap space more so that we can save the cost. And the second one is use the Spark UI thread dump. When we have a running Spark application, we can always use the thread dump in the Spark UI and keep refreshing that. And for the thread dump frequently appear in every time, that must be the bottleneck implementation. So here is the example. I masked the internal code, but basically the idea is that we find that some internal code in the most expensive job in our system repeatedly create the Java array. That makes the job pretty slow. So with the on-heap space tuning based on memory utilization stats and the bottleneck code optimization, here is an example about how we optimize the job. We can see that we can reduce about half of the resource consumption for this job after we tune the on-heap space, and after we optimize the bottleneck implementation, we can save more, about another 30 to 40% of cost saving there. So next problem is we cannot just assign engineers to tune every job every day for our customers. How we can scale this practice? The problem here is our users are not really interested in saving the cost. They have so many urgent tasks to finish. They need to run their business logic successfully. And there are also many complicated operations needed for capping the cost and at the same time meet the SLA of every job. So how we do this? We are basically developing something called managing the job set. The customer just give the input to us as the total budget, SLA of each job, and the set of jobs sharing a chunk of budget, and we can provide them the initial optimal configuration for their job. And then we can do some automated or semi-automated cost monitoring and tuning for their jobs. This is something we are currently working on with our customer. So, summary of this talk. We have our solution to address the cost efficiency challenges in Pinterest is basically in 3 layers. First, we improve the cost and performance observability, and we build a comprehensive observability platform with the real-time metrics and also event logs to help us to surface different root cause of the cost issues. And we build general solutions in platform-wide. For example, we optimize our shuffle performance with the remote shuffle service, and we save our cost allocation with the burst-aware memory allocation algorithm. And for those very, very expensive and critical jobs, we apply the fine-grained cost management strategy. And to scale this practice, we are developing managed job set to provide the managed experience for cost budget for our customers. So yeah, that's pretty much about my talk. Thank you very much. Happy to take questions.